Okay, dear student, let us see what is there in this question. Blue light of wavelength lambda is incident on double slit. The light from double slit falls on a screen. The student measures the distance between 9 successive fringes on the screen to be 15 centimeter. The separation of the double slit is 60 micrometer. Okay, so this is the wavelength lambda. The separation between the double slit is this. So this is small d, this is small d, okay, like this. The double slit is 2.5 meters away from the screen. So this distance is also given, which is capital D, and capital D is given as 2.5 meters. Explain the pattern seen on the screen. Obviously, the pattern will be the interference, and we will not be considering diffraction. See, you can never get rid of diffraction in the first place, but if we have to consider diffraction, then the fringe width b should also be given, but the question is silent about b. So I believe that we will not be talking about the diffraction here, because they are not talking about b anymore. They are only and only talking about uh, the d, which is the distance between the two slits. Definitely they are only talking about interference. So we will say our answer will be that there will be this will be the central bright fringe, and then like wherever the constructive interference is taking place, there will be bright fringe, and otherwise there will be dark fringe. So pattern will be somewhat like this, and there will not be any major difference in the intensities of the maxima, because we are not considering diffraction. Couple of these things, and then the answer can be written. Whenever it is written explain, you need not to go into mathematics, you can just explain it. Okay, so you just need to write 2 or 3 sentences there. Okay, I will show you the mark scheme later. Let us move to the next part also. Calculate in nanometer the wavelength. Okay, so we want to find the wavelength, and we know that fringe spacing formula in the case of interference is given by lambda capital D divided by small d. This is fringe spacing. Fringe spacing means the gap between two fringes. So if this is the bright fringe and this is another bright fringe, this and this is the gap that we're talking about. This is the spacing. So how can we find this spacing? Now it says that there are 9 successive fringes, so one will be the central, 4 fringes can be on this side, 4 fringes will be on this side. Overall there are 9 fringes total. So the distance is 15 centimeters. So I can clearly say that the distance between one will be equal to 15 centimeter divided by 9, isn't it? So it will be 9 only. No, 9 fringes there. So there is a catch here. Just a moment. 1, 2, 3, 4. So 1, 2, 3, 4. 1, 2, 3, 4. 8. There will be 9 fringes, but the gap is 8 times the distance. Like this is 1, this is 2, this is 3, this is 4, and 4 fringes on this side. 3, 4. 1, 2, 3, 4, and 1, 2, 3, 4. So 9 fringes means that there are 8 fringe spacings there. So this spacing can be found by 15 centimeter divided by 8, not divided by 9. So be very careful here. So that will be the spacing, and accordingly we can find the value of what? Wavelength. So wavelength is equal to 15 centimeter. So that will be divided by 100 into 8 into small d divided by capital D. So small d is this 60 micro, and capital D is 2.5. So that is 2.5 here. I think this is the equation that we have to use, and we will find the wavelength from this. I will not be using my calculator again. Let us go to the mark scheme and see if they have done the same thing. Yes, this is question number 3 only. 3a. Mention interference. Bright fringes occur when the light slit arrives in phase, and dark fringes occur when the phase difference is pi. It means like destructive interference is taking place, there will be a dark fringe, and wherever the constructive interference will be taking place, there will be a bright fringe. And they're clearly talking about interference, they are not talking about diffraction, but practically you cannot get rid of diffraction, and every time the pattern will be looking like this is the central fringe, and then it will be lesser. Okay, so it will always be like this. So just a moment. In interference it will be like this is the diffraction pattern like this. Clear? So this kind of a pattern is more practical and it should come out to be like this, but we are not talking about diffraction, we are not considering it. That is why we will say that the intensity is not reducing. Kind of, we can say that we are using narrow slits. So if there are narrow slits, we usually ignore the effect of diffraction. Clear? So this is exactly the same thing that I was telling you. Now spacing is 15 centimeter divided by 8. That is this, and this is equal to the same formula that I told you. Lambda is equal to ds by d, and from it you would be getting the answer 450 nanometers. Exactly the same thing as we did. Let us now move to the next part. A B1 and B2. The student moves the screen closer to the double slit and repeats the measurements. The instruments used to make the measurements are unchanged. Discuss the effect this movement has on the fractional uncertainty of the value of the wavelength lambda. See, these kind of questions which are related with topic 1, they are highly confusing, but there is a pattern that you have to follow, and then you can clearly give the answer to these kind of questions. So what is the step number 1? Step number 1 is that we are going to write the formula that we have used first of all. So the formula used is s is equal to lambda d by d. What are we going to find? Only the wavelength. So lambda is equal to SD divided by capital D. This is the actual formula that we have been using. On this, we are going to apply our science of uncertainty. So what are we going to do? Um, he is changing D. So D is definitely changing. Small d is not changing. Small d is the distance between the two slits. That is not variable. Only the screen is moved closer to it. Only the screen is moved closer to it. So d is showing some change, but the small d is not having any change. Obviously, s will be having a change, isn't it? Like, because provided that the wavelength is constant that you're using, so s will also be changing. But anyways, so this can be used to create an uncertainty equation. We have been using the propagation of error in that topic, if you remember. So this equation will be delta lambda by lambda is equal to delta s by s plus delta small d divided by d plus delta capital D divided by capital D. So the first point that I want you to note is everything is added. We are not subtracting the denominator. We're not subtracting anything. All the fractional uncertainties of all the variables involved have been added. Now clearly small d is not changing, so delta d is 0, so this part clearly becomes 0. So we are like not dependent on that. So delta lambda by lambda is dependent on this, provided that we are not making any mistake, because they're saying that we are using the same instrument for measuring the fringe length or something. So let us say this is not changing anything, it is directly proportional to delta lambda. So if we are decreasing this value, so d value is decreasing, but because the instrument is the same, so delta d will remain the same. What is delta d? That will be the least count of the instrument. So the instrument is millimeters, like the least count is millimeter, so your delta d will be 0.001 meter, isn't it? Like it is going to be that only every time. But small d is decreasing, it means this value overall is going to increase, which means that the fractional error in the wavelength is going to increase if we are reducing the distance between the slits and the screen. So my answer is that the fractional error, a fractional uncertainty in the value of lambda is going to increase. Let us see what is there in the mark scheme. As the measurements decrease, the fractional uncertainty increases. Fractional uncertainties are additive. All the fractional uncertainties are added, whether capital D is occurring in the denominator, even then it is added. So fractional uncertainty of in the wavelength is going to increase. This is the proper explanation for this. The topic name is propagation of error, if you want to refer to that. Okay, let us now move to the next question, C. The student changes the light source to one that emits two colors. Okay. If the earlier question was not easy, not difficult, and the students were not that the question was not problematic already. So there are two colors that now that are going towards the slit. So one blue light, the wavelength is lambda, and the red, which is 1.5 lambda. Predict the pattern that the student will see on the screen now. Obviously, the superposition will not take place because the wavelength is different. So we can say that it will not be the superposition or something. What will happen is like this. Now, fringe spacing is directly proportional to the wavelength. It means in the case of blue, there will be some fringe spacing. In the case of red, the fringe spacing is going to be 1.5 times the earlier one. It means that central fringe will be there for red as well as for blue. The central fringe will be there. Like let us say this is the pattern for blue. Let us say this is the pattern for blue. Now what happens? In the case of red, it becomes 1.5 times. So this is 1, so it will be 1.5 here. Somewhat like this kind of pattern will be there. And 1.5 times means that this pattern is going to become wider. The fringe spacing is now going to become 1.5 times more. So it will be wider. Okay, simple. So we will say some positions will be there, like the central bright fringe, where red and blue both are having the maximum intensity. So there will be a different color there, red and blue. They are going to mix up. So some other color will be there. But there will be places where red will be red and blue will be blue. They will be separated by the distances, and the fringes are not overlapping each other. And on it, the red fringe width will be more, so the spacing will be more, so they would be occupying more space. That will be the correct answer for this. Let us see what is given in the mark scheme. Blue fringe is unchanged. Red fringes are farther apart than blue by a factor of 1.5. At some points, the fringes coincide and the color is becoming purple. Exactly the same thing that I told you, but yeah, this answer is a bit more organized. Okay, let us see if there is any other part that is remaining. No, this is the last part for the question number 3. Thanks for watching the video. Thanks for joining the YouTube channel. Please share the video with your friends and see you in the next video. All the best. Bye.